A professor is interested in determining if freshmen receive similar grades to upperclassmen in her class. We have a sample of 60 freshman grades and a sample of 50 upperclassmen grades, and we have the data in our table. We want to find out if the proportion of students receiving the various grades differ for the two class levels. So this is a test of homogeneity because we want to find out if the proportions of people receiving the different grades is the same for our groups or if it's different for our two groups. So our null hypothesis here is that there would be no difference, so the proportions receiving A, B, C, D's, and F's are the same for the two groups, and the alternative is then that there's some difference in those. For this test of homogeneity, we're going to need to find all of our expected counts to compare them to our observed counts, which are given in the table. To find our expected counts, we need to take the row total times the column total over the total sample size. Total sample size is 110 since we have 60 and 50, but we need to find out the row totals and the column totals. So for the A's, if we add 10 and 12, we see there are 22 people. For this group, there are 38, and we continue that for all the rows and all of our columns, and I'll add all those values now. Now that we have all our row and column totals, we can start finding our expected counts, what we call our E's. For A's for freshmen, we'll take our 22 times 60, that's the row and column there, over 110, and we get an expected count of 12. For the B's for freshmen, we'll take 38 times 60 over our 110, and we get 20.727. We continue this for all 10 cells, and I'll add all of those to the table. Now that we have all of our E's for all 10 of the categories, we can find our chi-square test statistic, which is the sum of our O minus our E squared divided by our E. So for freshmen receiving A's, we have O of 10 minus E of 12. We square that over E of 12. For the next group, we have an O of 22, an E of 20.727, so we square that and divide by 20.727. And we continue that throughout the rest of the table. So you'd have 10 total terms here, with your last term being 3 minus 5.455 squared over 5.455. And notice all of those expected counts, the E's that I added there in red, are all at least 5. So our condition for this test to be valid is satisfied. Our sample is large enough that all the E's are greater than 5. So if you go through now and you add up all 10 of these terms, you will get your test statistic, which is equal to 8.506. And we want to look that up in our chi-square table. The degrees of freedom we use is the number of rows minus 1 times the number of columns minus 1. We've got 2 rows and 5 columns, so we will get 1 times 4 and use a degrees of freedom of 4. So we'll look for 8.506 in row 4 of our table. And what we find is that it's between 7.78 and 9.49, so that our p-value is between 0.05 and 0.10. This is greater than 0.05, so we will fail to reject our null. This means that we do not have significant evidence that there is a difference in grades for these two groups. And our two groups here are the freshmen and the upperclassmen. If you would look at the counts in the table, you'll see some differences. There are going to be differences in how many grades are dished out to the different categories here, which are freshmen and upperclassmen. What we're saying, though, is based on this data, if you were to look at the whole population of students who took this professor's course, that you would find out that there isn't any difference in the percentage of people in the two groups that receive the different types of grades.